Nice to see everybody here. Well, or see y'all's names, I guess. Okay. So, alrighty. So this first time we've done this. So hi, I'm Matt Kerrigan, and here I have with me Matteo Pilato. We are in the Creating Images from Text group to those fellows who are currently in the program. We started our program about 2 weeks ago. And we're now doing the paper we're talking about today is a transformer-based framework for multivariate time series representation in learning. Yeah, as I said, I'm Matt Kerrigan. So let's jump into it. So the TLDR of what we're about to talk about the paper is the TST is a BERT-inspired transformer model applied to time series data. So basically the goal of what this paper is trying to accomplish is to make modeling time series like modeling NLP. And we'll get more into like what that means here in a minute. So first off, you know, if you've never worked with time series data, I personally haven't done a ton of it with it myself. You know, so it might be kind of new. So it's some of the concepts going on. So let's go over that briefly. So basically, time series is like your modeling changes that happen over time. I think that's pretty intuitive. It's typically used for modeling more like high resolution updates in practice. Like if something is longer, I think often more like simple models that are based on more static features get used, but you can obviously model any time scale. Typically the models are doing either like regression, classification, or forecasting. So predicting like the next values, like regression, you're taking like a time series of values and then regressing against some value, and then classification, I think people are familiar with. Oops. And then the common use cases, I think everyone thinks of like stock price prediction, like revenue prediction, weather forecasting, etc. So like what is kind of like the field of time series models of today? So like the old school is kind of like just the world of acronyms of similar but slightly different acronyms. It's because the models are very much related to each other. Almost all of them have the word autoaggressive in it. They're like each individual one isn't that complicated, but like there's like little adjustments that happen in each one of these that come with like different assumptions and have different use cases. And this is a big reason like why time series is considered kind of a more difficult field, is because you kind of have to like know a lot. It reminds me of like the old school days of like statisticians and like the 1,000 variations of like linear regression and like how to use the exact right one for the exact right situation. Then compare that to like more modern methods like LSTM and RNNs, ResNet, something called Rocket that uses some form of like convolutional neural net to do this stuff. The one I see a lot of was just dynamic time warping distance metrics, some sort of like matrix factorization or neural net using this as a distance metric to optimize. And there's problems with these methods compared to what we're about to demonstrate. But like the basic gist of like the big problem in time series modeling is that you don't have like a more general tool to work with. And this is kind of reflected in like the sentiment amongst data scientists when it comes to time series. Like, why are time series so hard to handle? WTF is time series? What's the point of time series, right? And actually, I have my own personal story with this, which you're not allowed to tell people about this because it's embarrassing and really degenerate. So like, it's just like conceptually, they're old rusty models that nobody wants to learn. So this is a real story from when I used to work like very early in my career at a Fortune 200 company, where instead of like learning a time series model, I just did like a for loop and trained a logistic regression for different time scales and deployed like something like 6 or 12 models, and just told like marketing and like the other teams just to like work with that. They were predicting like whether a lead would convert like using different timescales of information. And I just did this. And it worked pretty well, admittedly. Then I got away with it, but like this is stupid, and don't do this. Use the thing we're about to show you. So as I said, like there's no free lunch. There's never any free lunch, but like in time series particularly, you don't have like a model that's just like a log reg. So like just try that, you know, before getting into like a more specialist model. You know, so like methods that like work really well are often pretty complex. They have high computational cost. One interesting one is there really isn't any current model that can exploit GPU resources, so they don't scale all that great. Labeling is really expensive. I think the sentiment around like labeling is expensive is primarily from the world of finance and like stock market prediction. Particularly, you need to have a high amount of expertise in order to like label, like, I just think of the candlesticks because I'm pretty naive when it comes to stock market stuff, but you need to have someone who's pretty an expert in that stuff to be able to label like this sequence is like this kind of pattern, like this stock's doing such and such. Also, because most of, I think, the money that drives the innovation in this field is from the stock market, it's mostly for like univariate problems, so you're only like predicting price. And again, like the big problem is there's no really general use model. So enter transformers. So transformers like have been kind of all the rage lately. So I'm sure a lot of people on this call like certainly have heard of it, and definitely probably a lot of you have played with it yourself. But if you're not really all that familiar, transformer models, they've rapidly emerged as like the state of the art in NLP. And they use this like concept of like stacked attention in order to do that. There's a famous paper called "Attention is All You Need," which doesn't have any kind of the real traditional looking like neural net architecture. They're just like stacking attention on attention. And it has some unique advantages for time series specifically, at least compared to what the current time series modelings are capable of. So one thing is that it can model much longer sequences. And I guess like not even necessarily saying model much longer sequences, but much longer sequences well. Like, you know, look at an LSTM, it has much shorter time dependencies that it can actually like work with, whereas this, it scales a lot higher. It can learn multiple representation of inputs, so it can and compare those, learn multiple relationships between each input. Whereas a lot of the current time series models kind of learn like one global view, and this can kind of mess things up. And yeah, attention is applied many times, allowing for more complicated representations, basically, like I said, and you can parallelize computation. So the author's vision is to basically just BERT, but for time series. So BERT is probably one of the most famous kind of like base architectures for like NLP-centric transformer models. And just like straight from the paper is our work aspires to generalize the use of transformers to a framework which allows for unsupervised pre-training and be readily used for a wide variety of downstream tasks. This is analogous to the way BERT works. One interesting kind of thing that isn't exactly clear in the paper is they use this term downstream, which I personally, at least, typically associate with like a large pre-trained language model being fine-tuned for some downstream task by like another user. Whereas like in time series, that's kind of a weird concept, is like I guess one wouldn't imagine that you could like pre-train a model on a bunch of different, like all different kinds of sorts of time series, different extremes of values and different purposes, and it would like work well. And that's not what they do in this paper. It's just proposing a unsupervised pre-training methodology that allows you to learn a representation of a particular time series data set and then fine tuning for whatever the task you're using is for. So this idea of like downstream tasks, as if there's like many of them, is kind of weird because you're probably just using it for a single purpose, but it might be the author's vision that is to actually have something like this one day. And they have some other language in the paper that sort of alludes to that, but they're just not quite there yet. And they didn't upload any big pre-trained model or anything that would indicate that. So that's what we can gather from it. So yeah, and like to talk about a little bit kind of like what that vision would look like in NLP. It's like, if you're not familiar, there's something called Hugging Face, but technically it could be any model repo if another one really existed, where you download your big pre-trained model that, like, say Facebook or Google has already trained for you. You fine tune it on a data set. In this case, I use Yelp as an example for predicting ratings, and then you get monies. So that's kind of like how that works, and potentially the vision that the authors had for time series as well. So how does it work? I'm going to turn this over to Matteo, and he's going to do an excellent presentation.
Thank you, Matt, and hi, everyone. So basically, the author proposed two different approaches. The first approach relies only on supervised learning. And on the left side of the slide, you can see the generic architecture the author used to implement this first approach. At the bottom, you see the input data, which is a multivariate time series, which the first step is to normalize them across each variables in order to have zero mean and one standard deviation. Then the second step consists in projecting the input data onto a d-dimensional vector space which is the same vector space of the encoder, and for this reason is also called the model dimension. Then, in order to also preserve the information regarding the location of each value in the sequence, we perform positional encoding. Here, the authors decided to use a different approach used in the paper of the autoencoder, and they use trainable approach where the weights assigned to each variable are defined by the algorithm itself. So once we have applied positional encoding, the use becomes our queries, keys, and values for the multi-attention layer in the encoder. And this is the place where actually the model learns the relationship between the preceding and succeeding sequence of data, and also the relationship between different variables in the multivariate time series. Then after the self-attention layer, we have skip connection, batch normalization, a feed-forward layer, and another batch normalization. For the one who were a bit familiar with transformers, probably has already noticed some slightly changes compared to the original transformers model. In fact, the author here only used the encoder part of the transformers, and they also replaced the layer normalization with the batch norm because they discovered that the batch normalization worked well with the presence of the outlier in the multivariate time series. In the next slide, we display the unsupervised pre-training approach, which is the second methodology proposed by the authors. In this case, for the pre-training, the goal for the model is to learn how to reconstruct the corrupted sequences. And in order to do that, the authors decided to apply a stochastic mask schemes to the input data in order to simulate the corruption. The masking is based on a geometric distribution, and the segment of the masked inputs it is quite large compared to traditional approaches, because they discover that this was the only way to force the model to truly learn the relationship between the different values along the same sequence, and also the interdependency between the different variables. And another interesting point is that they use a customized loss function. In fact, they measure the reconstruction error between the original input data and the reconstructed one, only considering the mask observation. In the following slide, we represent an example of regression. In fact, after you perform unsupervised pre-training, you can add on top of the general architecture the layer you want, depending on the task you want to perform. Here in this case, the encoder generate a sequence of vector that are concatenated together, and then they pass through a linear layer, and this linear layer generate the outputs, which can be more than one depending on how many scalar value you want to predict. In the next slide, instead, we show an example of classification which is basically the same architecture as before, but in this case, we use a softmax activation function in order to have probability instead of raw values. Finally, in this slide, we also have imputation and forecasting. In fact, the same architecture that the author used to perform unsupervised pre-training is exactly the same that can be used to perform data imputation. And they also show that by simply changing the masking procedure applied to the input data, is it possible to perform different tasks. For example, here we have a deterministic mask, which is applied only to the values from a certain point in time. And with that, is it possible to perform forecasting? Now in the next slide, Matt will describe the performances of the models and also the implication of this new architecture.
Yeah, appreciate it, bud. Yeah, so the model performs pretty well. I think that, so here you can see like the traditional thing that you see in the papers where they bold how they get state of the art on all the things. I think the most important bit about this is that when the model is pre-trained before doing supervised training, we get state of the art, and it tends to do the best of all the models. Another thing that is to note about this model is that it seems to do really well in high dimension and really low in low dimension. I was supposed to put a note about which data sets here were high dimensional, low dimensional, but I forgot because I got caught up in helping someone else off today. So it does pretty well in classification as well. It's very similar. They get, I believe, 7 out of they get a majority of the data sets that they tested to be state of the art, again, with pre-training compared to other models. I think the other one that is still doing pretty well is primarily Rocket, and maybe XGBoost as well is still doing pretty comparably. Yeah, in certain cases, those are the two that seem to be the ones that compare the most. And these were kind of two generally the ones that were state of the art before this. But I'd say that at least when it's like Rocket and XGBoost, I believe they're both primarily for univariate data for the most part. That might not be true with XGBoost, but I'm pretty sure Rocket's for univariate data. So this model is much more flexible in that respect. I think this is the most interesting one, is about like the data requirements and versus performance. So you can see here with the unsupervised pre-training versus the supervised training, you see, and this is error here, so lower is better. You see the unsupervised pre-training, like by miles, is doing better than supervised as you add more data, but even at lower amounts, you see like quite a bit of jump in performance. And you can kind of see a similar thing with like how much percentage of the labels are actually available to the data set. You can see that it's pretty robust to like noise and like a lack of labels and data. So how well does all right? So training time. It's in the paper, and when they're proposing the problems for like the problems that this model will solve, they talked a lot about like computation performance versus like the top two here, like particularly versus XGBoost. I'm not actually convinced that training, at least particularly, isn't that much better. I imagine XGBoost is a little faster during inference as well, but it is pretty fast, and I think it scales complexity. Like the one thing we know about transformers, it seems to be true, is if you add more parameters, it will generally do a bit better. And that same kind of thing doesn't really seem to be true with XGBoost. So there's, I think, more opportunities for growth within the transformer paradigm, but it still does, train pretty fast. The one thing that the authors I wish they included was something to do a little bit more with like what actual inference times look like. Another thing to know about these models compared to the traditional language models is that it's much, much smaller. Like you're talking about parameter numbers within the hundreds of thousands. So it actually probably runs pretty fast. You might even be able to run it on CPU pretty efficiently. So that is, good to know, et cetera. So implications, I think earlier I kind of alluded to this entire presentation, is that the big benefit of this is that you don't have to make a bunch of assumptions in order to use a time series model, right? In order to train this model on time series data. You no longer have to be like an old school stats nerd to work with time series. Anyone who has experience with transformers in the natural language space could probably pretty easily transition to work within time series. There's obviously some things you have to learn, but like at least the modeling aspect, you're not like, you know, like falling on your face right as you get started. It probably will actually have some, it'll allow, I think, research within time series beyond just like stock market finance, where there's more incentives, to be a little bit more incentivized too. Whereas I think junior researchers just using the latest and greatest in transformer architectures can probably pretty rapidly reach state of the art. So there's going to be some people, I think, a lot more people who will enter this field now that this has happened. There's an unofficial implementation. It's okay. I think I tried playing with it a little bit, but you know, it's out there. To be honest, one could probably implement this from scratch themselves, you know, given like a week or so, maybe less if you're more skilled than I. But yeah, so if you want to actually go play with it, you just like look it up, or I'm not sure if someone's going to share these slides somewhere. You can go ahead and play with it. And yeah, so that's it. So taking